Alright, this is going to be our first video in our work and energy module. So everything that we're going to be talking about in this module corresponds to chapter 7 in the text, and so we can jump right into it here. Okay, so we're going to be talking about work and energy, and so we'll start off by defining energy. Well, maybe not exactly defining it, but just saying that loosely energy is defined as the ability to do work on something. So we're going to start by looking at work, and through looking at work we'll get a better understanding of energy, and then we're going to come back and talk about different types of energy later on in this module. Okay, so moving on to work, the everyday meaning of work and its scientific definition are somewhat different in a sense. So for work to be done in a scientific sense, we require that a force has to be exerted on a system or an object, and that this system or object or whatever it is we're talking about has to be displaced in the direction of the force that's exerted on it. So formally, we have our definition here in the form of an equation. We can see it here, equation 1. And so what do we have here? Well, we have work, and work is defined as the magnitude of the force being applied to the system times the magnitude of the displacement vector caused by this force being applied to the system, and then the cosine of the angle between them. Okay, and so if we just remove those absolute value symbols so that we're taking the magnitudes, we end up with this cleaner formula that I have boxed here. This is what we're going to usually use when we're talking about work. And down here I've just written out a sort of in words translation of what this equation means. So the work done on the system is equal to the magnitude of the force applied to the system times the displacement experienced by the system times the cosine of the angle between the force and displacement vectors. Okay, and so I think the easiest way to get a feel for what work is to maybe just do a couple of little mini examples. So these examples don't really have any calculation going on. They're just more sort of talking about situations. So the first one we're going to look at is a person pushing a lawnmower on flat ground, and we're going to come back to this later on and do it with some more numbers at the end of this video. But for now, we'll just look at it, just sort of to try to get some ideas of what's going on. So we can imagine. Let's imagine we have a person here. Person is pushing on a lawnmower. This is my lawnmower. It's got some kind of handle or something here. So the person's pushing on the lawnmower. They are applying a force. Maybe I'll draw this in a different color. So they're applying some force, kind of at an angle downward here, on the lawnmower. This is some force. And then the lawnmower is being displaced. The displacement of the lawnmower is in this direction, right? So the lawnmower is moving along in that direction. And so from our definition, well we know. I'll switch back to black here. We know that work is equal to FD cos theta. And so what are we really doing when we're taking this right-hand side of the equation? What is FD cos theta? Well, first of all, what's theta here? Theta is the angle between the two of these vectors. Okay, so that's our theta there. So what's the work done on the lawnmower by the person pushing here? Well, very simply, we would just take work. It would just be the magnitude of F here, so it's just the magnitude of this, times the magnitude of this, and then times the cosine of the angle between them. Okay, and what are we really doing when we're taking the cosine of the angle between them? We're projecting F. Basically what we're getting is the component of F that points in the direction of D. Right? This part here is F cos theta. Right? So that's the part of F that points in the direction of D. And so if we had numbers, we could easily do this calculation, and we will do that do that in the last part of the video here. But in this case, we can see that since our force is non-zero and our displacement is non-zero and our cosine of theta is non-zero, here we would have a work that is not equal to zero, right? There would be some work done in this system. Let's take a look at a different example though now. Okay, so in this example we're going to take a look at a person holding a briefcase walking at constant speed. Okay, so the key here is they're walking at constant speed. Okay, so here I'll try and draw another picture. We have a person, they're going to be holding, this is going to be my briefcase, so the person's holding the briefcase. Okay, so that's a pretty bad drawing, but you can imagine this is a person holding the briefcase, and they are walking with some constant velocity in this direction. Okay, so what's happening here? Well, we have a displacement of the briefcase. The briefcase is being displaced in this direction, and there's a force being applied on the briefcase by the person to keep the briefcase from succumbing to gravity and hitting the ground, right? So there's a force being applied on the briefcase in this direction by the person, and we have an angle between our force and our displacement here of theta. So is there any work being done on the briefcase by the person? And this is sort of where our natural intuition could kind of lead us astray. We might think, well, this might be a heavy briefcase. This person's carrying it at constant speed. They must be doing some work. Well, they're not doing any work on the briefcase. So why is that? So let's again write down our equation here. So clearly F is non-zero. The person's applying some sort of force to keep the briefcase from falling, to do some work against gravity here, or I shouldn't say to do some work against gravity, at least to counteract gravity. So there is some force. So F is non-zero. The displacement, well, they're moving, so there's clearly some displacement. So the displacement is non-zero, but the cosine of our angle theta, so cos theta, here theta equals 90 degrees. The angle between the force being applied and our displacement is 90 degrees, and so this means that cos theta equals 0. Right? And because of that reason, because this is 0, then we end up with no work being done. So as I said, this is sort of counterintuitive. We might think that, well, if this is a heavy briefcase and this person's doing all this or exerting all this force, keeping it up and moving forward, well, they must be doing some work. But there's actually no work being done, scientifically speaking, on the briefcase by the person. Okay. Let's take a look at another situation here. So we're going to look at a situation here where a person is carrying a briefcase up some stairs. So I'm going to draw some stairs here. Those are not great, but you can imagine that these are stairs. And I won't draw the person in here. Maybe I'll just draw the briefcase. You can imagine that there's a person holding this briefcase and making it move in this way, right? So a person's holding the briefcase up, so they're applying some force in this direction, and the briefcase is being displaced. It's moving up these stairs in this direction. So that's our displacement. Okay. And so what is our theta here? Well, our theta is going to be the angle between the two of these, right? So theta here is this. And so is there work being done? Well, let's again write down our definition of work, FD cos theta. And again, F is non-zero, right? Because there's definitely some force being applied by the person working against gravity. D is non-zero. There is some displacement. And here our angle is not 90 degrees, and so cos theta is also non-zero. So yes, there is some work being done by this person bringing this briefcase up the staircase. Okay. I have one more example here, like a mini example, and then we'll move on to a couple of other things. So let's say we get to the top of the staircase with this briefcase, and then the person hooks the briefcase up to some sort of a generator with a line hanging down it, and the generator then lowers the briefcase. The generator is slowing gravity, pulling the briefcase down, and generating, say, let's say some electricity from this or something, right? So there's some force being applied by the generator to keep the briefcase from just plummeting to the ground, but it is displacing in this direction, but more slowly than it would if it wasn't attached to the generator. Okay, and so is there work being done in this case? Well, again, let's go back to the definition. Work is equal to force times displacement times the cosine of the angle between them. And so again, we do have some force. Force is non-zero. We definitely have some displacement. Displacement is non-zero. But now what's our angle? Well, our angle is this whole angle in here. Our angle is 180 degrees in this case. And the cosine of 180 degrees is equal to -1. And so what do we end up with? Well, we end up with a work that's negative, so a work of less than 0. So the work being done by the generator on the briefcase is negative. It's doing negative work on the briefcase, and so it's extracting some energy from the system. And we're going to take a closer look at all these ideas more carefully as we go through the module. But just be aware that work can be negative. There are situations in which the work done will be 0, even if your intuition seems to want to suggest that it shouldn't be. And so just keep those ideas in mind as we move forward here. Okay. And so I just sort of summed that up here. Clear cases where no work is done. If the displacement on the object having the force applied to it is 0, i.e. if d is 0, work done on the object is 0. So this is sort of like a person pushing on a wall, right? No matter how hard a person is pushing on a wall, if the wall is not moving, no work is being done on that wall by that person. So you can push as hard as you want on a cement wall or whatever. If the wall is not moving, you're doing no work on the wall. Okay? And if the angle between the applied force and the displacement is 90 degrees, as we saw in one of the examples above, this means that that there is no work done on the system. So the work again is 0, right? Because the force being applied to the system is 90 degrees from the displacement of that system, and again we end up with no work being done. So I'll just make a quick note here on the SI units of work. And then we'll do one sort of numeric example, and that'll be it for this video. So the SI units for work are going to turn out to be the same SI units we use for energy, which we will talk about a little bit later. And we can kind of see what the SI units for work will have to be just by looking at the equation. And maybe I'll write this in here, but I'll erase it after. So work equal to FD cos theta. Well, cos theta has no units. So this has no units, but our displacement has units of meters in terms of SI units, and our force has units of newtons, right? So we can see right away that we're going to end up with work needing to have units of newtons and meters. So what I've done down here is I just broke up the newtons into kilogram meters per second squared, and basically that's what we have here. We have 1 kilogram meter per second squared times a meter, right? Because we're getting an extra meter from the distance, ends up being Newton meters, which is what we just saw, and we call this sort of collection of units joules. So these collection of units, this kilogram meter squared per second squared, can be written as Newton meters, and it can also be written as joules. So when we talk about energy or we talk about work, we're going to talk about it in terms of joules, and joules are just this collection of more elementary SI units. Okay, so let's take a look at a quick example here with some numbers. And so what are we looking at here? How much work is done on a lawnmower by a person exerting a constant force of 75 newtons at an angle of 35 degrees below the horizontal, pushing a lawnmower 25 meters on level ground. So this is very similar to the mini example that we did above. So I'm going to draw it again. We can imagine we have our person here. They are applying a force on a lawnmower like this. And I'm going to draw in a different color here again. So again, we have some force being applied here. We have some displacement in this direction, and we have some angle between the two of these. I'll call it theta here. And we're given some numbers. Well, we're told that theta is 35 degrees, right? We're told that the angle of the force being applied is 35 degrees below horizontal. So you can imagine that this is horizontal, and our displacement is horizontal, right? The lawnmower moves 25 meters on level ground. And so we know what the force, or at least the magnitude of the force is. We know that's, that was 75 newtons. And the distance that we're traveling here is 25 meters. And so we can see quite quickly that right away we're going to end up with some work being done on this lawnmower by this person. From our equation, we can just substitute in numbers, and we end up with 75 times 25 times the cosine of 35 degrees. If you do that calculation in your calculator, you're going to see that 1,540 joules of work was done on the lawnmower by the person. Okay, and it's important to think about these quantities of work sort of like we think about forces, right? It's important what the systems are and how they interact with each other, right? So in this case, the work being done, there's work being done by the person on the lawnmower, and the amount of work done by the person on the lawnmower is 1,540 joules. Okay. All right. We'll move on to other topics in work and energy in the next one.